Okay, well, this is not ideal, but we're just going to roll with it. So, in this video lecture, I am going to start chapter 25. The active notes should be posted on Google Classroom. And I'm just going to go through the slides. And I mean, I could spend a lot of time on this lecture because I really like stars. I love the life cycle of stars. It's just unique and interesting to me. But anyways, chapter 25 is titled Beyond Our Solar System. Okay, so we started off with astronomy, talking about our solar system and our planets. And then we kind of took it a step further and, looked at the sun and some other objects in our solar system, like comets and meteoroids. And so now we're really going to take a step back and take a look at galaxies and stars that are very far away. So we're moving beyond our solar system here. So chapter 25.1 is properties of stars. And so I'm going to talk about what can we learn by studying star properties? How do we measure the distance of stars? What are factors that determine how bright a star looks at night? And then talk about this Hertzsprung-Russell diagram, which is part of your assignment. So, introduction. Our closest star is the sun. It is 8 light minutes away. And when I say that it's 8 light minutes away, that means if you were traveling at the speed of light, 300,000 kilometers per second, it would take 8 minutes to go from the sun to the Earth. So the light that you're seeing from the sun is 8 minutes old. Our next closest star is Proxima Centauri, and that's 4.3 light years away, which means that it would take 4.3 years for the light of that star to reach us. So the light that you were seeing from the star is old, okay, 4.3 years old. And when we look at other stars, it takes billions. It might take billions, okay, even million. I mean, thousands, millions, billions, depending on how far it is. But what I'm trying to say is that the light that we see in the nighttime sky is old. It's almost like we're looking back in time because maybe that star has gone through supernova, or has become a red giant, or has fluctuated in its life cycle, but we haven't seen it yet because the light hasn't reached us yet. Now, when we look into the nighttime sky, on a given clear night with the naked eye, you can see about 6,000 stars. And some of you may be familiar with groups of stars in the nighttime sky, and they're called constellations. Okay, so there are 88 constellations in the nighttime sky. However, you only see roughly about half of them in the northern hemisphere because there are constellations that are in the southern hemisphere that we don't see at all. And there are constellations in the northern hemisphere that if someone lived in Australia, they wouldn't see at all either. Okay, so like they don't see the Big Dipper. We do. We don't see the Southern Cross. The southern hemisphere does. So there are 88 total constellations. A lot of them are named after Greek mythology, or some kind of culture reference, to the people that studied the nighttime sky. And it's not always Greek mythology too. Sometimes I was just like reading a book about this, how like the Chinese, they named stars or constellations after their folklore, their stories. But now we've kind of collaborated and what I'm trying to say is Greek mythology is more popular, right? So constellations, groups of stars in the nighttime sky, like the Big Dipper, Orion, Cepheus. My personal favorite is Cassiopeia. So here is the nighttime sky, okay? Hercules, Ursa Minor, let's see, Ursa Major, that's the Big Dipper. Cassiopeia is one of my favorites. I was trying to see if I could find Orion. It would be kind of towards the southern hemisphere. Oh, there it is. There's Orion. Because we only see Orion during the winter months. Okay, so when we look at the nighttime sky like Orion, so here's the constellation of Orion, it looks like all the stars are like roughly in the same plane, but that's not the case. They are far, like the distance of those stars is far away. And they may seem like they have similar brightness, but that's not always the case either, because some of these stars might be supergiants or they might be closer to us, etc. So we don't see Orion in the summer. because the Earth is over here in that revolution around the sun, and so the sun is actually blocking out where the constellation Orion is. But in the winter months, like right now, you can look at the nighttime sky and see Orion rise and set in the sky. So here are just some constellations that are visible each season, specifically towards the northern hemisphere. I just wanted to list this in case someone out there is an amateur astronomer who likes to look at the nighttime sky, like me. So, and like I said, the constellations do change seasonally. So here you can see in the summer, you see a different set of constellations, and nighttime sky, roughly the same time. And over here in the winter, you see a different set of constellations. But the ones that you see throughout the year are the ones that you did in your crossword puzzle, circumpolar constellations. So those are the ones that you can basically see every single night throughout the year. Okay, I'm going to talk a little bit about the speed of light, okay, because I mentioned it in the first slide here. Light, if you're traveling at the speed of light going from Earth to the moon, it would only take 1.2 light seconds. We already discussed 8 light minutes here, Earth to sun. Earth to Mars, 12.7 light minutes. Okay, if you've ever seen the movie The Martian, when he is trying to communicate through the rover back home, there's that delay. And that is because that signal is traveling roughly the speed of light. And so he had to wait, a while just to communicate messages back and forth. Earth to Proxima Centauri, and if we were to travel to the other side of our own galaxy, 52,000 light years. Our galaxy is big. We'll talk about our galaxy in this chapter. So how long would it take us to go to Alpha Centauri with our fastest aircraft? So right now our fastest aircraft is the X-15 rocket plane that travels roughly 1 mile per second. So to travel 1 million miles, because we'd have to travel this, would take 11.5 days. To go 1 billion miles, 31.7 years. But to travel this distance in an X-15 rocket, 801,708 years. Now, spacecrafts that orbit Earth travel faster, roughly 17,500 miles per hour. That number does fluctuate. Apollo 10 achieved higher speeds, but that's because it was falling through Earth's atmosphere, and so it gained acceleration. So it's not traveling through space, but 164,922 years. So yeah, things outside the solar, space, there's just a lot of space in space. So let's talk a little bit about characteristics of stars. All the knowledge that we know from stars comes from the electromagnetic radiation that they give off. And so we study radio waves, microwaves, infrared, visible light. Oh, what's above that? Ultraviolet, X-rays, and gamma rays. Okay, everything we know about the stars is from electromagnetic radiation. Okay, just so you know, my son is probably going to interrupt me here because I'm making this the morning of that e-learning day. But anyways, we can determine properties of stars, such as color from that visible light it's given off. But from color, we can also determine its temperature. And then we can also determine its mass. Hey, buddy, can you give me a few minutes while I finish my video lecture? There's no school today. There's no school today. Okay, so Mrs. Paul's going to have us do some things. But I got to finish my school stuff, okay? All right, I'll be up in a minute. Okay, so star color and temperature. All objects do emit and absorb radiation, and the planets in our solar system, they reflect some of the light that hits them from the sun. Stars in our nighttime sky are black body radiators, which means that they absorb electromagnetic radiation, and then they give it off at certain frequencies. Okay, so you guys absorb electromagnetic radiation, and you absorb it, and some of it is reflected off. Okay, we tend to reflect ours off in infrared. But the radiation that's given off by stars depends on their temperature. And how do you determine temperature? You look at the color. Okay, the color of the star can tell us the temperature. And so I know this sounds kind of weird, but blue stars, okay, they have that shorter wavelength, higher frequency, higher energy, they're actually our hottest. Whereas with red stars, longer wavelength, okay, red spectrum, coolest. So over here I have colors and then examples of stars in our nighttime sky. And then roughly the surface temperatures in degrees Celsius. Now, I think our book might use Kelvin, just so you know, but Kelvin and Celsius are roughly the same. Stars also exist in different shapes, and so if you ever see a diagram where they have letters at the top, they're trying to describe the size of it. So I just thought I'd include a picture of that, but you don't need to know that. But color, you do. Color, blue is the hottest, red is the coolest, yellow is in the middle. Now, stars in space tend to orbit or go around other stars. Our solar system is not like that, okay? Our star is by itself. But when we look at other stars in the nighttime sky, we notice that they actually are paired with another set of stars. They actually orbit each other. And so we call them binary star systems, or even multiple star systems. But binary just means pairs of stars pulled together, pulled toward each other by that gravity. And more than 50% of the stars are either binary or even multiple, which means more than two. And so when these stars are going around each other, they will eclipse each other, like one will go in front of the other. And we can use that information, okay, with Doppler shifts, with speed, the rate of it eclipsing the other star to determine its mass. There's math involved, okay? But finding the mass of a star is obviously the most difficult to find, but temperature and color are not. And then, what is it made up of? Well, we use a spectroscope for that. So here is an example of just structure of a sextuple system, TYC 7037891, and their orbit. So here you can see we have a binary, isolated here, binary, but these two are going around each other, but these two are going around these four. And so it's like a system within a system within a system. And obviously, the orbits of these are not to scale, but just know that there are multiple stars out there that exist together. So when we measure distance to stars, we use something called parallax. And parallax is actually something you are familiar with. You just didn't know that it was called parallax. If you ever go through a gun safety course, okay, and you're trying to find your dominant eye, you're using parallax and you didn't even know it. What you do is you have your hands up and you, like in front of you, I should say, not up. And you form like a little hole, like with your thumbs, you like overlap your fingers and your thumbs so that you can like look at an object with both eyes. And then you would close one and then you'd open the other and you close one to find that dominant eye. But when you close one and you open the other, things shift, right? And so that shift is called parallax. And what you do is you measure that shift, okay? And then using a little bit of math, you can roughly determine how far away that star is. So how astronomers use it is they will take a picture of a star in the nighttime sky at one point in Earth's orbit around the sun. And then 6 months later, they'll find the same star and they'll take another picture. And what they'll do is they'll compare the background of the stars. And they notice that nearest stars have the largest parallax angles and distant stars have the smallest parallax angles, okay, which means that when you close your eyes, that object, that whatever you're focused on, doesn't move a lot, whereas nearest stars do. And you can totally test this out. Like I'm looking at the door handle of my office and it shifts, roughly about like, I'd say 3 inches, okay? But then when I focus on a poster on somewhere on my children's playroom, that shift is a lot bigger. I would say like 5 inches. So here's what I mean by that. Here's the star that you are looking at, and you see it in the nighttime sky. You take a picture of it, and you can see that the star is behind this blue square. Okay, I know this is not like what it is like in space. But then 6 months later, you see the same object, you take a picture, what's in the background, and then you would measure that shift, okay, the distance between those two locations. Now, this is a more accurate picture of the object in space, and there's the background stars. And so here it is from A, here it is to B. You measure that distance, you do a little bit of math, and then you can roughly figure out how far away that object is in space. And so we tend to use light years, the distance light travels in 1 year, for that, because AU is too small kilometers and miles are really, really, really too small. So anyways. Okay, stars in the nighttime sky, yes, they're giving off light, and some stars are brighter than others. And so I want to talk about two definitions that describe the brightness of stars. Apparent magnitude is the star's brightness as it appears from Earth. And there are three factors that control apparent brightness: how big it is, how hot it is, how far away it is. And we tend to use numbers to rank this apparent magnitude, where the smaller the number, the brighter the star. And sometimes these numbers are actually negative. And so if you have come across a negative number, wow, that is a really, really bright star. So here is a diagram showing stars in our nighttime sky, like Betelgeuse, which is part of Orion, Polaris, which is the North Star. Barnard's star was part of our Doppler assignment. The full moon, okay, negative 12.5. The sun, negative 26.8. And so that lower number shows brightness, okay? All right.
Is Earth brightness?
Earth reflects light. We don't give off light. We just reflect it.
But our sun comes in Earth.
Right, the sunlight from the sun comes to Earth. Yep. So absolute magnitude is how bright the star actually is. Okay, so in the other one, the apparent magnitude, it's like viewed from Earth. But let's say distance was not a factor. Okay, let's see how bright the star actually is. Like from the same, like if we were to place all the stars at the same distance, now which one is actually bright? Take distance out as the factor. So two stars that have the same absolute magnitude usually don't have the same apparent magnitude because of that distance. Okay, obviously the further one's going to appear dimmer. And so what they do is they determine the magnitude if it was at a standard distance of 32.6 light years. Why they chose that number? No idea. I guess I've never investigated that. But values lower than 5 are brighter than our sun. So here's a diagram that shows you the difference between apparent brightness versus absolute brightness, or apparent magnitude versus absolute magnitude. Okay, so magnitude means brightness. So the apparent brightness is as it's viewed, okay, from planet Earth. Okay, if you had a candle super up, close, and a campfire a half-mile away, oh, they have distance here, I'm dumb, 2 meters versus 100 meters, obviously the candle is going to appear brighter because it's closer to you. Whereas with absolute brightness, okay, now they're saying put both objects at the same distance. Now which one's brighter? Okay, now you're going to say the campfire. So one more Venn diagram to show apparent magnitude versus absolute magnitude. Brightness as it appears to the observer, brightness from the same distance or a certain distance, and that distance is 32.6 light years. Oh, I guess now I know why it's 32.6 light years, because it's roughly 10 parsecs, which is another unit that astronomers can use.
Hey, Mom.
Yes, buddy.
If you see the Seven Sisters, that's a part of the Devil Tower.
Is it?
It's a story about the Devil Tower.
Okay, well maybe we'll have...
The Devil Tower was growing, and they were getting up to the top, and it was growing. They got into Earth, and they turned into the Seven Sisters.
Okay, well maybe we'll have to look more into that. Okay, so one more thing I'm going to discuss is the Hertzsprung-Russell diagram, or the HR diagram. And what it does is it shows the relationship between brightness, in this case absolute magnitude, and the temperature of the stars. And when you graph out stars according to their brightness and their temperature, it shows that most of the stars that are in the solar system belong in an area called the main sequence stars. They're just average stars. And anything above main sequence stars is where you find your red giants and your supergiants. So this is the HR diagram. Here I have my brightness, okay, luminosity, 1 is the sun. And here I have my temperature in degree Kelvin. Okay, I shouldn't even say degree Kelvin, it's just Kelvin. But when you plot stars according to how bright they are and their temperature, you see this nice long train of stars, and you can see the color variation going from hottest to coolest. And here's our star, just an average star in the middle of the main sequence. Now things above it is where you find your supergiants and your giants. And obviously we'll talk about these stars in depth, like what does it mean to be a supergiant or a giant. Okay, and then things below that we'll talk about white dwarfs. Buddy, I really got to finish this lecture so I can get it out to my students. Some other things in the nighttime sky are variable stars, and these are stars that fluctuate in their brightness. And I actually didn't know that this existed until I came across your textbook. And so like they're called Cepheid variables, and that means that the stars get brighter and fainter in a regular pattern. And what they actually do is they fluctuate. They increase in size and then they shrink. And I don't know if it's because they're unstable, but I found a animation on the next slide that I'll show you. Novas are basically like the supernovas or novas, a sudden brightening of a star due to an eruption because that outer layer is being ejected at high speeds. And so that star might be bright for a few weeks and then it will slowly return back to its original brightness. So here's what I mean by the Cepheid variables. They actually change size, where luminosity is low and then it increases and it brightens and then it decreases and then it increases in brightness. Now where they are on the HR diagram is they vary from the main sequence to possibly a giant, okay? Because they're increasing in size and then they go back down. So I thought that was kind of cool. So I found this animation on Wikipedia. I couldn't find one really anywhere else, but just how it fluctuates in size, increasing and decreasing. And as it's increasing, its brightness is also increasing. Okay, Betelgeuse, which is a red star in the Orion constellation, is fluctuating in brightness. Some are hypothesizing that it may go through supernova here soon. But yeah, they are closely monitoring that star in the Orion constellation. Some other things we see in our nighttime sky is interstellar matter, like dust and gases. And so when you come across a cluster of dust and gases, we call it a nebulae or a nebulae. And if the nebulae is close to a hot star, it can either illuminate or emit or reflect that light. So there are two types of bright nebulae, emission nebulae and reflection nebulae. Emission means that it's mostly made of hydrogen gas. It will absorb the ultraviolet radiation from that hot star and then transform it into a visible gas, or it will fluoresce, it will glow. Reflection means that it will reflect the light from nearby stars. So here it absorbs it and emits it off, and here it just reflects it. So here's what I mean by this is emission. You can see it's coming from the hot stars like within it, and here you can see it's being reflected off. It's reflecting off of the nearby stars.
So why is that? Why is it just so big purple and just running through the Earth?
Probably because of the composition of the gases and maybe possibly the EM spectrum, but it's kind of pretty. Now there's one more type of nebulae out there, but it's not a bright nebulae. They call it a dark nebulae. And this is interstellar matter that's not close to a star. So it doesn't absorb or reflect light. And so when we look at them in space, it just looks like this dark region, this blob, if you will. So it's seen as starless, dark regions when we look at them. And that's all we really know about them. So here's reflection and emission, and then our dark nebula. And that does it for 25.1. Now what I'm going to do is I'm going to drag the homework over. And I think I'm just going to give you a work day. I'm going to need to restructure what we cover for chapter 25. Good chance because of everything, this might be an open book test. And this is for the year 2025, so for future lectures. But here's the homework, okay? It is a book worksheet. I'm going to see if I can post the book online for you guys if you don't have it. But if you don't have your book, no worries, because guess what? You can do the last 2 pages without your book because it's about the HR diagram. So here's an HR diagram where it talks about luminosity and temperature. And it reads this little, make sure you read this paragraph because I think the first two questions are found in that first 2 paragraphs, or that first paragraph. But number 3 says, what's the approximate surface temperature of the sun? So you would find the sun, okay? And then here's temperature. So you would just draw a straight line down and you would say, roughly 6,000 K, okay? Number 4, is the surface temperature of white dwarf stars higher or lower than your red supergiant? So here are my white dwarfs. Here are my red supergiants. Wow, they're way over here, 20,000 K, whereas my red supergiants are, 2,000 K. So I would say that they are higher. And you continue to answer questions using the graph. Now, down here, number 13, kids always mess it up. It says plot the stars A through E. Okay, so that means you actually have to plot these on the HR diagram. Letter A is 6,000 K, luminosity 10 to the negative 1. So 6,000 K, luminosity 10 to the negative 1. So I'm going to put A like right by our sun. Okay, then it says plot B, 20,000 K, 10 to the 6. So here's 20,000 K, 10 to the 6. So there's my B. B is a blue giant. And you're going to do that for the other letters. And then you're going to tell me the color. So A was by my sun, so I would say yellow. And the type of star, I would say, is main sequence. These are my main sequence stars. And I would do the same thing for B. That was part of my blue giant, so I'd say the color is blue. And then what type of star? I would say blue giant, or you could say giant, and I'd, give you credit for that. But I'm pretty sure tomorrow's going to be, actually, I'm just going to declare it a work day so that people can catch up. I hope to see you tomorrow, and I hope you're safe out there. Okay, so that does it for 25.1. I know that was very long with all the interruptions, but I do appreciate your patience. Have a good one.